live programming Bitcoin in Rust with myself, Gary Kraus, and Pleb Lira here. How you doing? How you doing tonight, Pleb Lira?
I'm doing great. I'm actually on my fasting Mondays. That is,
Fasting
I have a plan
Mondays.
to I have a plan to fast every Monday. Yeah.
Wow. Okay. What? Interesting. Is this like a New Year's resolution? I take it.
I did a fast like on the first of the year, so that was a Sunday. That
Yeah.
lasted like through Monday night, so around 40 hours. And then I remembered a friend of mine used to fast once like a day a week. So
Right.
then I started today. So let's see
Okay.
the effects of that. Yeah, fasting's great. So I want to keep it consistent.
Yeah. I'm experimenting. I've heard all kinds of uh, good and bad. Mainly bad if you're looking at the establishment. But carnivore. I'm trying. Like
Nice.
I've eaten nothing but animal product since the beginning of the year. Um, First couple days were weird adjusting to. I've done like low carb keto before, but anyway, I've adjusted now, and if having steak for dinner is like fantastic because it happens all the time. Um,
It's great. It's liberating, right? Once
right,
you realize that one of the tastiest foods is also one of the healthiest foods.
right, exactly. So, but we're not here to talk about appropriate diets or health fads or healthy ways of living that may or may not have been done for millennia before modern science, we'll call it.
Exactly.
But
We're here to talk about programming Bitcoin.
you're damn right we are. And I had some fun. I don't want to say on my own because that's just sad to think about sometimes. But I did have some fun on my own experimenting. Actually, shout out to Hunter Beast, who runs a Telegram channel called Rust and Bitcoin. And I mean, it's been a fantastic sort of little community of people sharing tidbits in there. So I've been sharing in there a little bit and trying to answer some questions of people. And yeah. But, I shared some of the things in there that I was learning. Um, the first of which was, I guess, the modulo operator in Rust does not work like it does in many other programming languages. And I think maybe Java's one of the only other ones, like Java, C, maybe C++. Um, but it was super confusing because I was getting some errors. And I guess let me pull up. Well, let me ask you: have you delved into the programming Bitcoin since we last met? It's been a while. My last stream was a complete and utter failure. It was a solo stream. I was like, I think day 2 of adjusting to no carbs, and I was just super exhausted and like just could not think straight at all. And so I think I ended it at like 30 minutes in. But what have you been up to?
Keto fog. That's
It
keto
was,
fog.
yeah, it was pretty bad. But I'm feeling a
The,
lot
the
better now.
keto. Wait, I know that the right term is the keto flu.
Right,
What's called. Yeah.
right.
Anyway, I was working on chapter 3 on elliptic curve cryptography, and I was
Okay.
just coding the section for scalar multiplication. I just finished that.
Scalar
It's not like
multiplication.
crazily ahead of it, but it's at page like 48, 49, 50.
Oh yeah. Okay. So you're getting a little bit ahead.
Mm-hmm.
Nice.
Yeah, I was building on chapter 3 a little bit.
I haven't gotten to this part yet, so I don't even think I've read this part. Let me see. Where's my bookmark at? Yeah, I've read beyond that part, but not much beyond it. Um,
And
but
also, yeah, I was also figuring out how to build the test suites in Python.
did you had some luck with that?
Mm-hmm. Yeah, I was just like messing up, like importing a module that I thought it was part of Python. It was actually part of the books kit, the book script.
Oh. Okay.
So that was good too.
Yeah, that's that can be. How did you know that it was a module import that you were missing?
Just try and error, like just testing a bunch of different things. And
Right.
when you Google a module name and nothing comes up,
Be-
probably it's probably
because
doesn't exist, right?
well, it's because it was from the book, right?
Exactly, yeah.
Huh.
Yeah,
Okay.
silly me, silly me.
Well, did it? So Jimmy Song, when you're watching this, maybe include that in the book somewhere. Was it in the book? Did the book? Does it call out in the book that you need to be using this module?
It does in the code examples. It's the helper module. So in the
Oh,
code
yeah. Okay.
examples,
Yeah.
yeah, it shows.
It's in there
Um,
then. Never mind, Jimmy. Okay. Cool.
yeah, it doesn't make it fully clear that it's in there, but since yeah, we're doing it a little differently. We're not following the Jupyter notebook all the way. We kind of
Right.
so then yeah.
So,
Anyway, it's solved now, which is great.
cool, man. Well, yeah. I'm glad. I'm
And
glad.
you're really throwing a wrench in it by doing it all in Rust, which is amazing.
Why is that throwing a wrench in it? It's making it. I thought. I don't know. Maybe better.
I guess a good wrench, like making adding a great twist to it,
Yeah. Somebody was asking. I
do
need
do
to.
it in a better way.
I should hit them up in this Telegram. Actually, somebody was asking. Oh yeah, they were asking if there's a book, programming Bitcoin and Rust, and there's not. So maybe at the end of this series, we can, there's an opportunity there. There is a market demand of one customer, and where there's
Build
one, there are more.
build it and they will come.
Right, 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 right. So we'll see. But first, let's finish the book because I think we might be at this for a little while if we maintain the pace. My goal is to maintain, like, to cover everything that, even if we work ahead, like you and I, my goal is for the stream is to like cover the whole book. So even if we get ahead in our own studies and stuff like that, I'll maintain this master branch that I'm working on, to just be in lockstep with, what it is. And what I'm hoping today that we can go over is I'll do a comparison of my branch. We'll look at my branch compared to the master branch and the changes that I've made. And we'll talk about them, right? And we can, just have a discussion about like what it is. And that might be a better format. I don't know. But we're gonna try it out today.
Mm.
First, let's see. There we go. All right. Cool. Advertise. I tagged you on Twitter. I am taking a hiatus from Twitter. Just FYI, if you try to hit me up. Try and do the month of January. Just stay off of Twitter as much as possible. I've tweeted 2 things so far, just because I wanted to share them out. It's like a Bitcoin 101 presentation that I did is now on YouTube. And then I tweeted out that we were going live tonight, as well as I did a little like. I had a thought just randomly as I was sitting there watching some unicorn show with my kids. And so I jotted down some notes and put it on the internet for everyone to comment and critique. But yeah.
I saw that you posted along with the invitation to join the Twitch.
Right.
Uh,
Yeah.
so just detox, just social media detox.
Just detox. Yeah. And I'm doing this sort of like challenge thing where I got to read a book every day. And so the time that I would usually doom scroll on Twitter is now reading a book, which is the Fiat Standard. I'm finishing the last couple chapters for moving into something else. But let's get into talking about code, because that's what we're ultimately here to do.
Yes.
And let's see if there's a good way. I want to think there's a way to compare with Working Tree, and let's see how that goes. Oh, perfect. Okay, yeah. So this is cool. By the way, if you're using VS Code, this is an extension. You normally don't see all of these other add-ons, I guess, or extra things. But it's called GitLens, and it's like, as you can tell, with 19 million downloads. It's a pretty good extension. Um,
Wow.
because it gives you basically everything, like all of this. It gives you all these extra, looking at that file history and the different branches and everything. It's a very clean way to look at Git within VS Code, in my opinion, right? Other people might prefer
Nice.
something different, um, but yeah, let's check out what we changed here. So this was something. Well, we'll get into that. But basically, I had to figure out. We'll start with the field element, right? We'll start with the basic field element. Does this make sense when you look at Git diffs like this? Does this make sense to you?
Yeah, I was playing around with this the other day, like
Okay.
comparing two different files.
Okay. All right. Perfect. There's some of the format changes in here as well. I think on here, I've got the wrong formatter set up um, for this. I want to say, maybe I could do format on save. That might help. But like the default formatter is, may or may not be the right thing. Let me just check.
Mhm.
Default formatter, yeah, none. So Rust Analyzer, which is another wonderful extension, and it's actually you can use it with other development environments and like other editors, not just VS Code, but yeah, Rust Analyzer is like the de facto. I think they even deprecated one of the other plugins that VS Code had available. But that should work now. Anyway, let's talk about what I changed in field element. Do you want to talk quickly, like just a quick reminder of like what's a field element?
I can do that. I don't know if I'll have the most succinct explanation, but a field element is a group of numbers that restricts. It's a set of numbers that restricts the full complete field of elements, like real numbers, to a set amount of numbers. So it's usually set by the maximum number, which is what's
Order.
the name? The order. Thank you. Which is usually
And
a
just
prime number.
and just to clarify, you are describing right now a finite field of which a field element is one of those numbers.
Ah, that's correct. Thank you.
No, yeah, no worries. But yeah, yeah.
So a field element is part of a finite field, and a field element, uh, there are many operations that a field element you can apply to a field element, like addition, multiplication, exponentiation,
But
and all
what's
of those no, go ahead.
no, yeah, you're about to
All of
say.
those they have specific ways that they work. They and they all work because of the modulo function, which makes these field elements stay inside finite field.
Right. Yeah. So I guess like the TLDR is like a field element is an element in a finite field that is limited by the order of the field, which is a prime number if you have a finite field. And then you do something called modular arithmetic, which you're essentially doing normal math like A plus B, except now you're moduloing by the order of the field or the prime. And that's the magic piece and there's like a couple other like fun tricks that kind of keep it all within there. And somehow you can always get zero from a certain way of exponentiation. Right? Yeah, we're gonna go with that. That's a word. All right, cool. Yeah. Nice.
Yeah.
So, right, updated field element. Oh, this is kind of weird. Okay, so this is the reverse of what I wanted it to be. So give me just a second to see if we can't. Let's check this one out. we're going to switch to this branch. Oh, it's because we have changes that were made. That's fine. So yeah, we'll switch to this branch. And now, all right, so now we're on the Gary Dev branch, and now we can compare this with the working tree. And now it should show the way I want it. Yeah, okay, cool. So on the right are the changes, and on the left are the are what we had before.
Okay.
So nothing really up here, just formatting changes.
There's some refactoring, like some U size became U64.
Yeah, so U size is, it's like, it will, depending on what architecture you compile towards, like, so if you compile it toward, like, it kind of like varies on how whether it's a U32 or a U64. But we can just go straight to the docs, and it should have a better explanation of that. But at least that's my understanding. Yeah. So on a 32-bit target, it's just kind of like a different size, right? So CPU architecture, right? You have 32-bit and 64-bit are like the two most common ones. And so if you just put U size, it will just, like, whatever you're targeting to compile for, it will do that. So instead of leaving that up to the compiler, I'm just explicitly saying, like, hey, we're just going to run on 64-bit. It wasn't really, knowing that we're going to eventually come up to some really big numbers, I think 64-bit's probably the way to go. I didn't check Bitcoin Core, but if I had to guess, it's probably 64-bit. But that's a really good question that I should write down to answer later. So give me a second.
Yes. One thing that's for sure, the timestamps aren't 64 bits.
Why is that? Why do you say that?
Because there's that bug that's going to require a hard fork in like 80 years or so.
Oh.
Because Satoshi used 32-bit integers for the timestamp for the blocks.
Maybe it is all 32-bit then. Does it all fit in 32 bits?
Yeah.
It might. Anyway, our version.
Look up. Yeah.
Our version is gonna go 64, and so maybe this will be what becomes the hard fork in the future. You know.
Yeah, they'll use this code base.
Yeah, that would be
core devs of the future.
The core devs of that's what we're here to do, right?
Yeah.
Programming Bitcoin. So yeah, some other formatting changes. I had, once I changed these to be U64, there were a bunch of essentially method signatures that I had to update to be that same type, or return types, right? So had to update from usize to U64. So this is kind of where it got interesting. Previously, let's see, can we? I'm going to toggle word wrap. So previously we were doing this sort of, we were going by the book, but we were kind of doing some weird things. We were converting to and from different types because we were getting into the negative. And that's kind of where I discovered the interesting fact about Rust modulo operator, this percent sign operator, was because I was getting an error, like a multiplication, or no, it wasn't a multiplication overflow error. I want to say it was a subtraction overflow error. No. Oh, no, it wasn't either of those errors. I did get some multiplications and subtraction overflow errors, but I was able to address those. And I think that's in a different file. Anyway, this one was because I was getting the wrong answer. So when I was doing, when the code was running, I was getting the wrong answer, or it would have some sort of error where, it couldn't cast. So, we say 2 U size, right? Well, if it's a negative number, you can't make it a U size, or you can't make it an unsigned integer if it's a negative number, right? Because it's only positive integers.
Or a U64 for that matter.
Right,
Any unsigned.
right. And there was I was running into a case where it was not working. And then also with the exponent, I was getting an overflow because the numbers were getting so big, which is something that Jimmy called out in the book about, like, hey, these numbers are going to get really big, so you kind of need to do the special, modulo as you go sort of thing. And so this is what this refactor does, is it does some fun things with modulo, and all credit, like, I did not think of this myself. Credit goes to this wonderful gentleman, whoever he might be. But yeah, he was writing modular exponentiation in Rust, and it just happened to be the perfect perfect blog post that I needed to check out. And if you're out there and you want to check this out, you can find the link in the GitHub in this file on this comment. So fieldelement.rs. But it gives a great example of how like key exchanges are done, which I thought was like super cool, right? So it talks about just how you can basically, if two people, there's a secret that somebody chooses, and you put your secret in, and the other person puts their secret in, and you get these two numbers, right? So 460 and 622. And then you both put those into this math equation again, right? But using the same secret, right? Except you're using like the opposite, right? So if I was exchanging with you, you gave me this 622 number. I now plug this into my equation, and we end up with the same answer. And now this same answer becomes the shared key, right? So like I would do, 603 mod 289, where 289 is like my secret key or something like that. And as long as we're modding by the same thing, because I can share you the mod, I can share with you, the base number, and then I can share with you like the result of it. And then you do the same thing with your secret, right? And we just swap these two numbers. And then we run the same equation, except we insert as the base your answer for me and my answer for you. And we keep everything else the same. And now we get to we end up with the same result, which can now be, it's a shared key. I think I don't know if this is how Diffie-Hellman works, but it might be. Either way, it's now like I know how to do a secure key exchange, so that's pretty freaking cool.
And that's like being done with very essential elements, no, just numbers, and
right,
really abstract the concept, the basics of the concept.
Yeah, and I mean 17 is probably not the best shared key, just because it's such a small number. But if you can imagine expanding this out, right? Like brute forcing the number 17 would be relatively easy, like if you know it's a number. But if you make this much bigger,
like the number of atoms in the known universe.
Yeah. So anyway, it was super cool. But then the blog post goes into basically how you can sort of break down an exponent. So, if you have a number to the 11th power, mod whatever, you can just do like, 8 plus 2 plus 1 is a, like, you can multiply these together, and now it's smaller numbers to deal with, right? So you're not going to get an overflow by having just like a huge number.
Mm-hmm. And that's what you coded in that
Well,
software.
I didn't code it, but this is, I copy and pasted it here,
Mm-hmm.
which is why I linked out to it, because it's and and really what it does is, and he breaks down the code, which again, this is like beautiful. We can put this side by side with code and kind of go over it. Um,
It's nice. So it's kind of doing what the Python function does, which is always mod as it exponentiates.
right.
Is it that what's going on, or is it something else?
Sort of, not really. It's and it I don't know, because the Python function, because it's a function that's built into Python, right?
Yes. Uh huh.
So I don't know how that does it. It might be
Hmm.
fun to
Let
check
me
out.
look into the source. Yeah.
But it essentially it takes whatever the exponential is, right? So in this case, is that the exponential? Is 11 the exponential? I don't know. Whatever you're raising it to the power to, whatever that number is,
Exponent.
or
Yes.
the exponent. But it takes that and it breaks it down into, like, look at it in a binary format, right? So like 1011 is 11 in binary. And so what it does is it kind of it goes along each step, right? So it will shift to look at the next bit, and it will that's what this little double arrow to the side, what is that, greater than, yeah, double greater than, or whatever, is like a bit shift. So you're bit shifting one, so you're essentially removing
Oh wow.
one of the bits. So, right, so like you're removing this first bit, and then you're removing the second bit, and then you're removing the third bit, and it checks if that is so as long as it's not zero, right? It's checking if that is a one or a zero by modding it by 2, basically. Which mod 2 will also give you whether it's like a even or odd number. So if you mod by 2 and you get a 1, it's an odd number. If you mod by 2 and you get a 0, it's an even number. In this case, if you mod by 2 and you get a 1, it's a 1, not a 0. And then you're taking that and you're doing the multiplication and modding it. And so what it ends up being is you have, where is it? Yeah, so he even breaks it down even further. So result starts at 1 and the loop goes. And so result is 1, and you get 1 times the base, which I think in the example he gives would have been, oh, I guess he just doesn't give an example. But whatever you're raising to the multiple of, right? That's the base.
Mm-hmm.
So that times the base, and then you're modulating it, right? And then every
Yes.
time you're taking that result again and doing the same thing, except now because this is 1, the first result is 1. The second result is or I'm sorry, not the second result, the exponent. So the first exponent is 1. So you don't need to multiply it or raise it exponentially. And then 2, and then this one, because this evaluates to a 1, or because it doesn't evaluate to a 1 because it's a 0, then you end up skipping that one. And the end result is you kind of like break this up into chunks, and so that way it's smaller pieces.
Yes.
Anyway,
As opposed to if you scroll up, there was like 6 to the power of whatever number with 8 digits.
right,
So
yeah, yeah.
that's gonna overflow. There.
Yeah.
What the fuck is that?
Yeah, and here's the other thing is it tells you depending on how big the number is in binary, like how many bits you need to represent the number, that's how many steps it takes. So this is like more of like a speed thing, right? So the number 11 you can represent with 4 bits. 941 you can represent with 10 bits. And then whatever this number is, what is this? in the 982 million something. It's still only 30 bits.
Mm.
Uh, yeah. So that's
as opposed to 982 million times, right? Six
right,
to the power of-
right. And because we want a modulo, like we're keeping those numbers small. So
There's no need.
yeah, we're keeping those numbers within the field as we are moduling.
Or modding.
Modding. There we go. Perfect.
Maybe
So anyway,
very
very I don't know what's the word for like just the right thing at the right time.
elegant.
Yeah. So shout outs to Rob Cobb. Go give him a follow on Twitter. I don't know if I have yet because I'm not on Twitter. Here we go.
Right.
Oh, I'm following him. Must have followed him.
I'll follow Rob Cobb as well.
So that was kind of a refactor of the mod situation, because I was getting some weird answers I was getting a negative answer because the way Rust normal mod works was like it would just give you a negative answer. So if you're working, that was elsewhere. I'm sorry, that was elsewhere. This was more of a speed thing. There's another section in here where the negative modulo was throwing me off, but we'll go down to that next. Just some other formatting things. This is where the negative thing was happening. So it was in subtraction. And basically what was happening is when we took this number minus the other number, if it got a negative and then you modded it by the prime, it would give you back a negative. And it didn't like that because we're dealing with unsigned integers here.
Mm-hmm.
And so yeah, this was the other big kind of breakthrough, or not breakthrough, but like thing that I've read and learned about was there's this like remainder, basically Euclidean or Euclid. I have no idea what that second part of it means. I know it's some mathematical thing, I'm sure. If you're in the chat and you understand what that is, please let me know.
Least non-negative remainder of self.
It's done as if by the Euclidean division algorithm. But what it means in like simple speak is even if the difference is a negative, right? So say this was like the number was 1 and the other number was 54. So 1 minus 54 is going to be a negative 53. Well, when you mod that by a prime, the remainder is normally a positive number unless you're doing Rust, like the normal Rust percent sign remainder, because then it was giving me some weird negative number that didn't work out for the math that we were doing. But I guess
But if you do the remainder Euclidean, the rem Euclid, it will be a mod Python like mod.
Right. And I think it's I can't remember where it was. There was another sort of, it was a Stack Overflow answer. Actually, I posted it in that Telegram chat that I was mentioning earlier. Yeah, there's a whole explanation. Oh, no, maybe I didn't post it in there. But it was either way, it basically was just the way that Rust does it, and a couple of other languages do the modulo differently if you're using negative numbers. So, and it's been accounted for. What else do we have here? Oh, and this is another. What did I do? Was this just a formatting? Let's see. Yeah, it's just a formatting change. Nothing changed there. Some more formatting changes. So one of the things, oh yeah, I deleted some stuff over here. One of the things is, and I'll just go ahead and merge into master now that we've reviewed that kind of stuff, was one of the tests is still not working. So we're going to have to fix that. And it's not that it's not working, I just don't know the answer to it yet, if that makes sense. Merge branch into current branch, cool. Uh-oh, we have conflicts. Oh, okay. We're just going to accept both of these. This is just a VS Code configuration file that I set up to avoid some headaches. But if we go into our field element and we go down to all our tests that we wrote, we can run them and see that they work. Boom, passed. But if we run our point tests, we get 2 that fail. So it's the add self and then the add test are the ones that are failing right now. I needed to. Here's another fun thing that I did was I was trying to figure out points. Remember we were talking about no, I don't think we were talking about points on the curve, but I needed to figure out what points were on a curve, just like a given curve. Specifically using.
Oh, right. Yeah.
Yeah.
How to find a point in a curve? You have the x. What's y?
Right. And so I wrote a quick little script that was in the test that would print out all the points on the curve with a given prime as well. So I just iterated through, 0 through the prime number itself, and basically, if there's this catch unwind, which is, first of all, there's this set hook. So like set hook is you can do custom panicking stuff. So like if your code panics, you can do something custom with it. So I just did nothing, right? And then I did this catch unwind, which basically is like, hey, if this panics, don't like stop the program sort of thing, and created a new point. Because if you create a point with an X and a Y that are not on that curve, right? We were panicking, not throwing, but we were panicking, which may or may not be the way to handle this, right? There might be a better rustier way of doing that, but that's what we're doing right now. And so
you created every point independent if it was in the curve or not, and then filtered out the ones that were on the curve.
Well, yeah, and I use this match statement. So the result is it's a result type, which either is an okay or it's an error. So if it's an error, you just do nothing, and if it was okay, like if it worked, then I pushed it onto this list, and then at the end I just iterated over the list and printed it all out, and that's what this file is. So I've got a list of all these. Using prime 191, this is a list of all the points that are on the curve.
That's awesome.
So yeah, we need to do the add test. So this is okay. So this is when I picked 2 of these points, and what I was thinking of doing, instead of trusting the code, I was wondering if maybe we wanted to go through and add these points together ourselves, like manually, like show some work.
Okay, I'm down.
So let's bring up the formula for that.
addition.
Yeah. Point addition.
Let's see.
Ooh. Excuse me. So, yep. Because the elliptic curve point addition works over all fields. Same as usual. Same formulas we use to calculate point addition over real fields work with finite fields. So this was how we got to it, right? Was we had our 3 points. 0.1 plus 0.2 equals 0.3. You have to find the slope of the points. And then, wait, that's not right. Oh, there's a typo. Oh, interesting. Is that in the book too? Page 46?
You see it. It's supposed to be x2, y2 there. Right?
Yeah, okay, so in the book it's corrected. I got a bunk PDF. I do have a copy of the book. Support the author. Go buy the book.
With the author. I need to get my copy.
Anyway, that's coffee you're drinking?
No, water.
Perfect.
Yeah, water with salt. That's important in fasting. Is take lots of salt.
Oh, interesting.
I even came up with something last week. Okay, little nutrition break.
Sure.
It's the saltzer. You put salt on seltzer water. It tastes really good.
Yeah, I'm a big fan of seltzer water, so
It has to be like the unflavored one, but yeah, it tastes really good.
yeah, interesting. Huh.
Cheers.
Cheers. Yeah. I just I only use salt now with for seasoning on like my steaks. Interesting. But anyway, we're going to do some math here.
Yeah, so
And we
need those three bottom lines, right? The slope, x3, y3.
And we can use Python to do our math for us, right?
Mm-hmm.
So yeah, we need the slope. So slope equals. So what's our x1 or our y2 is going to be 58. So 58 minus 180 divided by 47 minus 57. So we got our slope, 12.2. And then, so now we get x3 is our slope squared.
Oh wait, so on the slope equation there, it's y2 and x2? It is, right?
It is, yeah. This is a typo on this PDF. Wherever I got this PDF from.
There, but also on P2 there. That's where I had seen it first. In the definition of P2, it has x3, y3.
Yeah.
So yeah, both typos, yeah. Okay, cool. Oh, so there's a. Oh, all right.
But we know the equation because we coded it. But the slope squared minus 50 minus x of 1 and then minus x of 2, which would be 47. But we got to remember to. Oh, you know what? We didn't modulo everything.
No, because we're doing fine field elements. Okay. Yeah.
Right. All right, so let's do 58 minus 180 mod, and I think our prime. What's our prime here? 191. Okay. So 191 is our prime. Mod 191. Negative 122. That's weird. You shouldn't be negative. Why is that negative? Is Python doing the weird mod thing that Rust was doing?
It
So
shouldn't. Yeah.
so all right. So what's 58 minus 180 first? So it's negative 122.
Yeah. So it should be 69. Should be 69. The result.
Is it?
I think so. Yeah, because you add 191 to 122. So it's not. Sorry, I'm tripping.
Do you add? Oh, here we can do this. Okay, so there's a mod function on the calculator. Minus 180. You're probably right.
Yeah.
Brilliant. So yeah, we should be getting 69.
Why is Python doing this? Because I didn't have any issues with Python giving like negative results on mod.
Yeah, I don't know. I wonder if it is the same thing. Are you using Python 3 or Python 2?
3, yeah, 3.8, I think. Yeah, no, my add function is pretty vanilla. Yeah, just the mods.
Hmm.
Or my subtraction as well. Yeah, no. So it always yields a result the same as the operator.
Yeah, it does. So how does that? I wonder why that's not called out in the book anywhere then. Do you remember that being called out in the book?
Mhm.
And that would be in finite field subtraction, right?
Mhm.
Oh, okay. Well, so maybe it doesn't. Yeah, I don't see it calling out. I mean, one of the exercises is. Well, let's just go look at exercise 3 then, and see what is what's put in there. So chapter 1, exercise 3. So yeah, this is. I mean, this is showing.
37, right? Like the second exercise.
But this is showing it's using the mod.
Just vanilla mod, right? Nothing
Yeah.
to deal with the negative cases. Hmm.
Okay.
Yeah, no. I did, yeah. I did many examples of that would yield a negative result, and he never did.
Really? Why is this happening to me? Clearly. Oh, geez. Of course, 1,000 advertisements, pop-ups. I want you to log in. No, thank you.
They're bluffing there. I know that website.
Consider, where do we find? Huh. So this is... So it talks about the mathematics behind a negative modulo. So negative 5 mod 4. That's not the answer we'll get. We'll run the code. We'll get the answer 3. It's because Python's modulo operator or returns a number having the same size. What happens behind the scenes if Python applies the distributed law of modulo operator.
I'm running the same operation on my REPL here, and I'm getting minus 122 as well.
Are you?
Yeah.
Huh. Well, we solved for this. All right, so we'll just have to do it semi by hand. Let's not go too deep down the rabbit hole on this one. Maybe it is addressed later in the book. I don't know. But we now know that. So it would be 69 divided by x2 minus x1, which is going to be negative 10. And so negative 10 mod 191 is 181. So 69 divided by 181. Oh, and then we need to mod that as well, right? Or we need to use the modulo arithmetic for that.
Oh, like a division.
Yeah, we might have to...
69 to the power of 181.
Yeah.
Something like that. That one, right?
Yeah. Yeah, this is...
Times 181 to the power of prime minus 2.
That's the... division. Finite field division. It is, yeah, it's minus 2. Good. Yep.
So 181 to the power of prime minus 2. That's what it is. Damn.
So this would be 189, right?
Mm-hmm. It's going to be a big number.
A little bit, yeah. So maybe... Oh, we need to... what's that Python function for the...
Yes.
Was it POW?
It was pow, number, exponent, mod.
So 181, 189, 191. Right?
Mm-hmm.
19. So then 19 times 69. And we're modding that one by 191. 165. So it goes all the way back to point addition. So that, or no, 165 is the slope. So 165 is the slope. Now we take 165.
165 is the slope?
165 is the slope, yeah.
Hmm.
Remember, we have to find the slope first to get to the x of our answer.
Okay. Mm-hmm.
And so, excuse me. So now we do 165 to the second, which we use this POW again. So 165 to the second with 191 as the modulo. We get 103. 103 minus x1, which is 57. mod, because that should be, that's a positive number. So 46, and then minus, so 46
-1.
minus 47. Oh, that's going to give us a negative. So when you go back to,
I think that's 190. But we can check to be sure.
this one?
If you mod by 191, yeah. Because you're gonna land at -1 and you just add
Oh, yeah.
mod as many times until you get to positive.
So 190. Okay. So 190 is x.
Okay.
And then y is, so we take x1 minus x3. So what is x1? 57 minus 190, which is negative. So what you said we do 191 minus 133 gives us the answer?
I think so.
If we're going to mod negative 133, you're saying it would be...
I think so, but I would check just to be safe.
Okay.
Yeah, it's like -133 plus 191. That's exactly the same thing. Yeah, but I've been wrong about this sometimes.
Mod 58. Perfect.
Okay.
Patterns everywhere. So that's this inside of here. So 58. So now we do 58 times the slope, which was 165. So 58 times 165. And then we mod that by 191. Gives us 20. And then 20 minus y1, which is 180, gives us negative 160. So 191 minus 160 is 31. So y for the answer should be 31. Are you ready to test it? Did we do it right?
I hope we did.
Hey!
Wow.
We did it! We're basically Bitcoin Core devs now. No, that was cool.
Wow.
That's well done, sir.
So you're...
Yeah.
Wow. Yeah. No. Well done, you. I was just like trying to.
No, you were chiming in there.
Nice doing by hand. That's amazing.
Yeah. I was saving that because I knew that this test was broken just because I didn't know what the answer was to, like, I know that these two are on the curve, but I didn't know what the answer was.
You added 2 points and they're both in the same elliptic curve.
Yeah. So and it's the Bitcoin curve. It's the SECP 256K1 or whatever.
No, yeah.
Which the A is 0 and the B is 7, right?
Perfect.
But nice. Okay, cool. That works. Let's we can commit that one up. Cool. So the next one, now we have just one failing test amongst all of these. I believe, yes, add self-test. Oh, and the add self-test, yeah, I had not updated this to be, to use the curve the new curve that we were using. So we'll just like grab one of these points. And it's because there was a different way of finding the slope of adding it to itself. Do you remember that?
Yeah.
Because it was like you had to find, what was it? There's a really cool diagram of it. this one right here. Right, because it's like when you're adding 2 points, it's the third intersection on the curve reversed or something like that was the answer.
And he had to use like limits and derivatives to find the slope.
Yeah, for this one, yeah. Yeah, so this a plus b equals, you find the slope and then you find where it intersects, and then it's the inverse, and then like this is the answer. So in this case, you're just the third. So if you're just adding this point to itself, this is the third point. So you got to figure out where this is, but then there's like special math for point addition for when p equals 1. So that's
when
cool.
P1 equals P2, right?
What's that?
For when P1 equals P2.
Right.
Special math for that.
Which
Addition when P1 equals P2. That's page.
Yep.
37. That's where you are.
And I think we have this already. I'm on page 46, but it's probably might be. You say you're on page 37?
I might be. Yeah, for adding the same point, but.
Oh yeah. I was at the section where it's just coding it, but this would just works. But this is the formula. Where is this formula here? And yeah, it's something about like it's calculus and derivative stuff, or deriving slope tangent to the curve, which I'm not super familiar with, so I'm not going to try to explain it. But
neither am
I. But we do get the formulas, and I think, if I'm not mistaken, we already had the formulas. We should have the formula somewhere. Yeah, here it is. So if let's toggle word wrap again.
If self equals other.
Yep. We're generating the slope, basically, using this formula instead of the other one.
But then you continue on the remaining, the rest of the same function, right? Because the rest is the same.
Yeah, and it's the same. They kind of condense this minus 2x1, just because the x's are the same. So normally it's minus x1 and minus x2. But
effectively the same thing. Yeah, that's cool.
Yeah. So it's really just the slope calculation was the only difference. But we now have these 2 points. Do you want to try to add these together manually again? Okay. All right. So we have this point 57. I don't know if that's a thing. Yeah, 57 and 180. So we have to take. So A is 0 in this initial equation. So I'm looking over here to find the slope. So we're basically taking 3 times. So it's x to the second. So we need to do 57 times itself times 57 mod 191. It's 2.
Yes.
That makes it easy. Okay. So then 2 times 3 mod 191 is 6. And then we take on the right side of that, so 2 of y1 So 180 times 180 mod 191. 121. So we have 6 over 121.
Which is 6 times 121 to the power of 189.
Right. So 120.
Yeah.
POW function, right?
Yeah.
121 to the power of 189 mod 191. So 30. So 6 times 30? What?
No. Oh, it was 2y, but you already did that, right? The 2 times y. You already did that.
I did.
180 times 180. No, wait. Y is 180.
180 times 180 is 121.
Oh, my. So wasn't it 180 times 2?
Yeah. Oh.
Right. Yeah. No, I didn't know.
This is why. Yep. This is it. This is why you're here.
180 times
So it's
2
169.
And then we'll do the power function, but 169 instead. Okay.
Right. So 169 to the 189th power mod 191 is 26. So then 26 times 6.
Mod 191, which is, I don't think the mod will change anything in the result there, because it's smaller, right? Yeah.
Well, 26 times 6, I think, is... Oh, yeah.
Yeah, so it doesn't...
156.
Yeah. 156, that's our slope?
156 is the slope, yeah.
Okay.
We'll just put that in a variable for now so we can reference later. So slope squared. So slope... But we would need to do pow of slope. Right? No, I'm sorry.
Yeah, no, I think that's it.
We don't need to, though, I guess. Like, I think we can still do this. And then mod 191.
Okay, yeah.
Is 79. So 79 minus... What is 2x1?
So 57 times 2.
114. So 79 minus 114. Which would be... Modded is 156. So 156 is the x value.
Okay.
And then the y is... So x, so 57 minus 156.
You want to mod that?
Yep.
Yeah.
So 92. 92 times... What was our slope?
156.
Yeah. Slope. 92 times slope. Mod 191. 27. So 27 minus 180. Gives us 38 for our final answer here.
Now,
Let's see if it works.
drum roll.
Hey! All right. Okay. Cool.
It works.
It does. Yeah. We're definitely It's so cool. It's been fun. I've done more of those. I've done more proofs, like writing out all the math and such.
Nice. Got the John Nash vibe.
John Nash. I don't know. I don't understand the reference.
just remember reminding me of like those huge whiteboards or blackboards to
Oh,
divide the
yeah.
equations.
Yeah, yeah, yeah. Yeah.
Or he would do it in the at least in the movie. You
Yeah.
see Russell Crowe doing it in the on the windows.
Oh, that's a beautiful
Yeah.
mind, right?
Uh-huh.
Yeah, 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 yeah. Or
The equations on the windows.
yep. I don't want to be that guy though. He like went crazy, didn't he?
Yeah, totally. And he reverse engineered his own schizophrenia.
That's crazy. I need to watch some of those movies like what is Good Will Hunting and
That's a good one.
Beautiful Mind.
Uh,
I need to watch those now that I'm an adult because I feel like I'd probably appreciate them more.
yeah, good call.
Well, that concludes our refactor of moving the points to using field elements, because now we have all the tests that we had for points, addition, equality, the identity point, right? So the identity point still works. That should bring us up to coding point addition. So we're here. This was Yep. Oh yeah, and this just talks about extending those tests. You did that already, right? So we're up to I think where you're at in the book then. So the scalar multiplications for elliptic curves.
Mm-hmm.
All right. So this kind of talks about the different. Okay, that makes sense. So scalar multiplication. Okay, this just kind of breaks down the whole. What is it? Associative property, where you can break these apart. Scalar multiplication is really hard to predict without calculating it. Good to know. Each point is labeled by how many times we've added the point. Interesting. Okay, so point division is not. Oh, this is okay. I remember this because this is talking about like this is the whole private public key derivation sort of thing.
Oh yeah, if you could, will you share that blog post that you were displaying earlier tonight, like about the secret, sharing the secret. I wanna look into that.
Okay. You want me to share it with you? Is that what you're saying?
Yeah, at some point.
Well, let me share it now before I forget, because I will forget. I will forget.
Yeah, so there is a reason why why it will be used, the scalar multiplication will be used as opposed to just regular multiplying by whatever numbers.
Why?
I think it's because they're gonna build what's called the cyclic groups or finite cyclic groups,
Okay.
which are kind of like it's exactly this page, like the final paragraph there. It's like when you add a point to itself, you
Yep.
keep adding it to itself, you eventually get to infinite or to infinity. And that point where it gets to infinity, that's when you found the end of the finite cyclic group. You see,
Oh, okay.
you're adding g plus 2g plus 3g plus 4g, where ng equals 0, which is infinity, where it's the point at infinity.
Huh.
And when
Okay.
you get to infinity, that's your set. That's your finite group or finite cyclic group.
Yeah. Okay. Why is this called a discrete log problem? Do, 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 do. Well, I don't think we'll go over that for right now. But yeah, so okay, so we have the addition. All right, so this is just tacking on multiplication because we have addition, but it's using. Is it just using the addition then for?
Yeah, even the way, yeah, the way I coded like exercise 4, for example, and I think that's,
Is that the
yeah, that's
next
what it is.
exercise?
Hmm?
So is that the
Sorry?
next exercise?
I think so. No, it's above it. Go back 2 pages. Like a, yeah, one before that, so it should be page 49.
Oh, okay. Yep.
It's yeah, instead of multiplying 21 like the last example, instead of multiplying that point by 21, I was just like adding 21, adding the point to itself 21 times, you know.
Okay.
And the reason why I was doing that is because, yeah, now you got me thinking, why not just multiply by 21? That would be a good exercise to compare the two results.
Well, we haven't defined multiplication either for our points.
Ah, oh, maybe that's why there isn't. We haven't at all,
Not in the code. No, not yet. So,
because maybe not a thing.
no, I mean I
It,
think it is. But let's keep going through here. So the scalar multiplication is adding the same point to itself.
oh,
Is the fact that it's very hard to reverse. Okay.
okay, so maybe that's why. That's why we're not multiplying, because yeah, it's not defined. Good point. Maybe
Right.
it's not. Yeah, it's yeah, this field is not as unlimited as the reals are. Like you can do any operation with any number. So for points, they can only be added or subtracted.
Or did we? Yeah, this is. Okay, this is. Well, we did define multiplication for field elements.
Exactly.
Um, result x s times p. So, but I don't think our code for field elements allows you to. Did we code it except where? Let me see. Multiplication. Oh yeah, we just had it multiply. Like you can't multiply by an integer. You have to give it a finite, or not a finite field, but a field element to multiply by. I don't know if that's gonna. I don't know if that works.
Multiply field element, not a point. That's what you're saying?
Yeah. So, let's see here. Yeah, when we define multiplication, it takes in the other like a self, right? So of the same type. So it takes in another field element,
Mm-hmm.
which I wonder. But that means you can't multiply. You can't multiply a field element by an integer larger than the prime, or even the prime itself, right? Even though you should be able to. Because like this right now for our code base does not work necessarily. Did we? When do you? Okay. I'm wondering when we code. We didn't code. I was curious when it's going to tell us to code the multiplication, Because I'm curious how this works in the.
The multiplication, this multiplication, the scalar multiplication.
Oh yeah, because it's never mind. It's just field elements. Never mind. That's why it works.
Mm-hmm. But it's points as well. These are points. But I think where it explains is the first sentence on that first
It
paragraph.
is a point. Yeah.
Scalar multiplication is adding the same point to itself some number of times. That's where the trick is.
Yeah, but I don't. We didn't add multiplication yet to point. So.
No, but it's basically like 6 times the point is point plus point plus point plus point plus point plus point. You know what I mean? You're just turning into addition.
Yeah.
You
I'm
got that. You're on board with that.
yeah, I'm on board with that. I'm specifically thinking about like the code. Like we have not written the code, and I think we need to almost go back and refactor our field element code because our field element code doesn't necessarily work with. Like it only works if given another field element of the same order.
Mm-hmm.
So if you wanted to multiply a field element by, if it's order 191 and you want to multiply by 200, you can't right now because you cannot create a
Okay.
field element where the value of that is 200. Does that make sense?
But, yes, but why would you multiply by 200? In which context?
It's a good question. I don't know. Yeah, that's true. I'm solely going off the fact that this is, it's allowing you to multiply by an integer, right? So taking a point and multiplying it by an integer, that's what this does. So P is of type point, S is a number or integer or whatever. But in our code base, it's not. Well, one, we haven't defined multiplication at all for the point, but for field elements specifically, we have not defined multiplication. And maybe did they talk about this in closing multiplication in Python? Okay, so yeah, when we were going over the multiplication method, it was multiplying field elements by themselves. Okay, so maybe we don't need to worry about that. Maybe I'm overthinking this, and we just need to worry about allowing for a point to be multiplied by an integer, like in these examples.
What you think is you do that by adding the point to itself by x. Yeah.
Right. Yeah. Okay.
Okay.
Um.
Yeah, which I was doing. Yeah, this is. Let me paste it on our. Yeah, I was kind of using a loop. Yeah, let me paste it on.
Is it in Python? Do you want to share your screen?
Or call me on the live share.
Oh,
I'll
yeah.
jump into your VS Code.
Yeah. All right, I'm gonna paste it over in Discord.
All right.
There you go, sir. There you go.
Notification. Open link. Open. Okay. Do you see me? Okay.
Yep.
I'll just dump it somewhere else and then we'll get rid of it. And just comment the whole thing out. So he offers like a bunch of examples of different multiplications.
Okay.
Create the point. And I started doing this, so when I'm creating a point, I define A and B as field elements from the get-go. So then when I create the point, I can just put A and B here instead of putting field element all the way, you know what I mean?
Mm-hmm.
So then these are the multiplications. So this is the number of times we're multiplicating x and y. So while I is smaller than the number of multiplications, I'll add p to itself. I'll add 1 to y. I'm just adding a bunch
Yep.
of points because I was following the process.
Okay, yeah, no, I get that makes
Yeah, that's
sense.
pretty straightforward. Right?
I mean, we could recreate that function as well. I don't know. Not to. My initial inclination is like the book didn't tell us to write it yet, so we're not going to write it. But also, like, we don't need to go exactly off the book, so maybe we just write it, just to write it.
Nice. So like to write the point multiplication function.
Right.
To add it to the point class.
Well,
Nice.
we are creating a function implementation, so we're creating, right? Because there's no classes in Rust. There are just structs.
Structs. Okay.
So let's take this because this is not the. Take this out. This is not the point field, or the point.
Oh yeah, we're in field element.
Yeah.
And you can you is it how he calls in the book, overload the class or the struct? So whenever you put a point and you set it to multiply to another one, it will use the function that you define.
Yeah, but we yeah, I mean, so yes, we did that with field element. My question becomes, I wonder if we can redefine the signature of the multiplication, right? So there's this, implementation block that we can do for point. So instead of field element, we would do it for point.
Nice.
But the other, we would want to have be what, an unsigned integer, right?
Mm-hmm.
So U64. I don't know if this will compile. Yeah, so it won't.
It's already telling you.
Well, it's because the multiplication. So this multiplication trait, requires you to implement a certain signature type. So it will accept another point to multiply 5, but you can't. So basically, we just can't make it. We can't overload it, so that way you can use the little asterisk star sign. We're gonna have to just create a method, a public function that's available for points, and we can call it multiply by.
Very clear.
Right. What would you call it? Multiply by, what's the the multiple. Multiple? Is that what you're multiplying by? Thank you. And then we're returning a point. So, looking at what you have here, we have to the point. So we need to find a function, let mute. There's probably an easier way to do this, but we're gonna. Yeah, let me try to think of this.
Yeah, so much stuff that's not needed here. It was doing. So it could multiply a set of different multiplications.
Yeah, I'm mainly thinking about this while loop.
Yeah. Let's get rid of the prints.
So we're thinking. All right. So we have I is going to be set to. Well, I will not be set to the multiple, but we can use we can start with. No, we'll just
multiple is where you stop adding.
Right. And we'll need to. So we need a holder for our result. That's mutatable, and that's just going to be. We need to pass in self. It's gonna be self. I don't know if that's right. We might fight the compiler here in a second, but we'll see how it goes. We're also gonna need to set again in your implementation. We need to set the I to be 2, because we're always gonna be multiple. You know, if it's by 1, right? So what do you do if we're multiplying by 1?
Gotta deal with that case as well.
It's also, I think, if
so then the while loop won't even start. Because if you're multiplying by 1, I is already going to be larger than 1. So I don't think the while loop is even going to start, right?
Right. Yep. Yeah. Good call. So yeah, while I is less than multiple, we take what the result plus equals result, or self in this case. And then I plus plus. I guess you can. Oh, yeah, see. Ooh, okay. And plus equal 1. So it doesn't like this. This is what I was saying. I think we're going to. Oh, it's complaining about return types. We just return type. All right, what is this? Cannot use plus equals. Okay, that's fine. So we're going to use result plus. That's just because we don't have a plus equals defined on our point. We only define just regular add. There's probably. Let's see here. The Rust add trait. There's probably another trait of similar name. Oh, add a sign. Duh. That makes sense.
Add a sign.
Yeah, that's the plus equal thing. So if we wanted to do an add a sign, we could do that, but it's fine. I'm not too worried about it.
We have to define the Is it
Yeah,
a trait? You would have to define the trait for this struct.
and it would. I mean, it would be the same add thing.
Well, not really. Yeah.
I mean, it would be pretty easy to implement. So we could do this. Add a sign for point because it's just like self equals self plus right hand side. Why is this not? This is yelling at us. Oh, duh, there's a dereferencing there. My mistake. Cannot add point to ampersand. Okay. We'll clone it. Alright, that's fine. That works. So I think that works. We'll find out if our test code doesn't work. Where were we writing that? Oh, it was up here. Multiplication.
Oh, yeah. And you can use add a sign. Yeah.
Yeah, look at that. Cool.
So when you're running the while loop and you have two variables there, isn't it gonna is self gonna update as the while loop loops?
No, self shouldn't update. We're changing result.
Ah, it's the other way around.
Yeah.
Okay. I never thought, yeah, because since I was using the same, didn't really matter.
But self is the point, like the initial point. So we're just adding every time.
To results, you're adding copies of self into the result.
Exactly.
Nice. Okay.
Yep. So let's write a test to test this, right?
Why is multiply by underscore?
Because we didn't.
Because it's not used.
Right. Yep. Dead code.
Yeah.
But we can fix that with the test.
Cool.
What should our test look like?
Want to do one of the ones in the book? So.
Sure.
Exercise 4, page 49. Maybe 4 times 47, 71.
All right, so let's get our point going.
Oh yeah, and we have the result, so we know where we have to land that.
Yes, we do. So what is it? The x is what did you say? 47. And our prime is 223. And 47 and 71. 71, 223. Then what is A? Oh man, let me do this.
Is that it here?
Yep.
And for A and B, you don't need the sum Was it some or none?
Some or none, yeah.
Or none,
Yeah, for A, it's just going to be a field element of 0, 223.
Seven. Oh yeah.
So that's our point. And then that's it, yeah. So then we just
Multiply it
result.
by any of those, yeah.
Well, let's create our expected.
Okay.
Would also be a point. So what's our? You said what are we gonna multiply by for?
Let's pick any. Let's do 6. So 139, 137.
Okay. Look at, yeah.
Oh wait. Sorry. I thought you were gonna just create a new point there.
Yeah, you're doing it the right way. Copy and paste, my man.
Like, oops, like this, right?
Yeah. And it was at
137.
Nice. So now, yeah, go ahead and type the rest.
So I want to do like point multiply by now.
No, point dot.
Oh yeah. 5, and then the multiple would be 6. And I wanna print this, or I just wanna run this operation.
No, we would do, so for tests we do assert equals, which let's assign. We can assign this to a variable. So let result, and we can just assert equals. Result and expected, or vice expected and result. And we'll see if that works. Fail. Uh-oh. See what happens here. Why did it panic? An assertion failed. So it got, the math was, so we put in 139 as expected, but our answer we got was 126.
Oh, so it was on the curve.
Oh, hold on. It was on the curve, but do you see? Okay, yeah, I see what happened here. Yeah. Do you see what happened?
Nope.
All right, so fine. So our code gave us an answer. It is not the answer we expected. We multiplied by 6.
So it multiplied like 1 less. Ready.
Yeah.
Multiplied by 5.
So there's a common saying in programming. It's like off by 1 is like off by 1 errors all the time. Oh. So this is one of those classic like off by 1 errors, and we can, we can debug it and we can see what.
It was like in the while loop. It was off by 1, yeah.
Yeah, and I think if we do this, I think that will fix it. But let's just check. Because if you add the equal sign, it just gives us one more iteration of the whole thing. And there we go.
Nice.
Cool, man.
Okay, no. We have a multiply by trait in the point struct.
No. No, we didn't use a trait, remember? Because the multiply trait would require us to have self as the type. So we just created a function. It's just a function
Function.
on the yeah. It's an implementation of a function on a point
On a
struct.
point. Struct.
Yeah.
Cool. Yeah. So the traits are like kind of the built-in functions that a class can have.
Traits are so okay. So that's a longer topic of discussion that I don't even know if
Hmm.
I'm fully qualified to discuss. But traits in
Good.
Rust are sort of ways. I don't want to say they're like creating. It's like creating a template almost, right? Um, and so okay, so this is it. Like an animal trait, there's like an animal thing, but if you implement the animal trait for a sheep, right? Because we have this struct sheep, then you have to implement new. You have to implement name. Like all these method signatures and stuff are like defined here, and this goes deep. Like Rust traits are sort of one of those topics that I haven't quite explored in depth
Hmm.
to talk about extensively, but it's a way to sort of make like a template sort of thing.
Okay.
Um, and so if we look at this is a trait, right? The add assign trait. So what is the trait? It's defined here. So add assign requires you to have a mutable self reference and then a right hand side. But right hand side is as defined as equal to the same struct value as self. So if we looked at like what was the trait we were multiplication, right? So mul or
Hmm.
mul assign. So again, it's we have this type that we need, the output. It requires type self, this. So when we implement that trait, you have to have that same signature that the trait defines. And because we were doing something outside of the normal, right? So in our example, we were doing the multiple. We wanted to multiply by an integer, like a normal integer, and not a point. Well, this trait wants you to have a point given, so it wants to multiply by a point. So because the multiplication is signed by the same type or whatever, if that makes sense.
Okay. Okay. Yeah. Sort of, but yeah, we don't have to go deep into it.
Yeah, no, it's late. I'm gonna call here anyway pretty soon, and we'll
Yeah. Exactly. Yeah. No, it's cool that we implemented this function. It's
yeah,
really cool.
yeah.
Yeah.
And we used your code this time. You wrote that code basically.
You, is this a refactoring to from Python to Rust, or like what you did, or a translation? How would you?
Yeah, translation. I would call that. Yeah, I would just call it translation. Like we just went from one language to another language. So yeah, translation.
It sounds like translation to me.
Oh yeah, yeah. I've done lots of translations.
Yeah. Yeah.
Um,
Awesome, dude. That was good.
yeah. Let's put a commit out there. So our changes are what do we do? So we did scalar multiplication for a point. What else? We also added the add assign. We implemented the add assign for point as well. And we clarified all these tests. Tests. Cool.
All right.
Boom. It's in the cloud. It's on GitHub. Cool. Well, thanks anybody that's been tuning in these past almost 2 hours now. We thank you for your continued patronage and nerding out on programming Bitcoin in Rust. I'm really excited to get to the point where we start doing transactions on testnet, but I think we're a little ways away.
Get in there.
But I'm excited to get there. Yeah.
Low time preference always gets there.
Right. Yeah. Apologize to anybody that missed us over the holiday season. But now we're back. We're back at it, and we should be here every Monday at 8:30.
Mm-hmm. Definitely.
At least until my new kid arrives. So we got to finish this in 9 months.
Yeah, that's a good goal for us to have.
Yeah, that might. Yeah,
Right. Yeah.
I think it's doable. Once a week.
We have to send a transaction on the same block that your kid arrives. We can schedule or a time lock. We
Yeah,
can have a
yeah, yeah.
time
Okay,
lock.
that's fine. I was just saying I'm gonna be pretty busy when that's happening.
Yeah, you're gonna have different priorities.
All right, everybody, have a good night out there. Stay humble and stack sats.
Good night, everybody.